All right, continuing the concentration discussion. In the last video, we talked about molarity. We talked about the ones that are most likely to come up in industry, like percent weight, percent volume, and percent mass over volume, okay? Now we need to talk about ones that are more likely to come up if you do like environmental things, like if you ever got a job for the EPA or reading articles about environmental waste. What we need to talk about are units that apply to really low concentrations. Like this is parts per million, which is abbreviated as ppm. Okay, so these are very dilute solutions. You would almost never order a solution from like a chemical company in ppm. Okay, you could dilute it to ppm, but you probably wouldn't order it as ppm. Okay, it's typically used to measure environmental waste. So if there's like a chemical spill in a lake, lakes are really big volumes, so the concentrations are pretty low, but that doesn't mean that you can't always just ignore it. But you need some way to keep track of it. So environmental waste. Okay. A ppm is a kind of a weird unit. What this means is that if you had 1,000,000 particles, solute and solvent, all mixed together, and whatever else might be floating in there, 1 ppm would mean one of those is whatever the contaminant is, whatever your solute that you care about is. Okay, and that's really hard to keep track of in terms of like number of particles. So we typically visualize it more like this. It's 1 milligram of solute per liter of solution. So these are low concentrations. So for example, like a typical water bottle, like the ones they give you when you go get your COVID test, this is ½ a liter. So basically 2 of these, you would need 1 milligram, which is 1,000th of a gram of that stuff dissolved into that volume, okay? There are some things that are toxic enough that at 1 ppm can cause a biological response and cause you damage, okay? But there are some things that are even more dangerous, and we use parts per billion. These are ppb. So this is essentially 1,000 times lower in concentration. And the way this works out, let's do it this way. 1 part per billion equals 1 microgram per liter of solution, and 1 microgram of solute per liter of solution. Okay, so it's essentially a milligram is 10 to the negative third grams, micrograms is 10 to the negative sixth. So this is 1,000th, this is 1,000,000th of a gram per solution, or per liter of solution. Okay, there are some things that are so toxic that this, you know, if you got like a 8 ppm or ppb concentration in your body, that it could cause cancer. It could cause some sort of negative effect. Okay, most things your body can filter out at these levels, but not everything. Especially like things like heavy metals, things like dioxin, which is like a byproduct of like plastic production. There was an article, this probably happened 15 years ago, where there was a huge dioxin spill in a river, I think it was in Michigan, and the concentrations were like 1,000 ppm, okay, or like hundreds of ppm, when, you know, 10 parts per billion could like be lethal to like people who are sick or infants or whatever. And there was this huge like environmental shutdown of this area. But, you know, it depends on the size of the body of water. If you drop, you know, a bucket full of dioxin in a pond, you're going to get really, really high concentrations, probably even in the molarity range, that are easily going to be noticeable, okay? If you drop it in like Lake Michigan, the biggest Great Lake that we have access to, you're going to get really low concentrations just because the volume is so big. So there are lots of times when these are very, very relevant. Unfortunately, if you're not in the environmental industry, if you're not working for the EPA or reading articles about environmental waste, this will probably never come up. Okay, not saying never, but it won't come up very often. All right, the last one I want to talk about is the weirdest of the bunch, which is why I left it for last. Okay. We learned about molarity, and we said that it is temperature dependent. It does depend on, like, if there's a temperature change, your molarity is going to change. We need something that is similar to molarity that has a temperature independence. So if the temperature changes, we can still use the same value. And this is something called molality. And for any of you who abbreviated moles as a lowercase m all through Chem 1, things are about to get real complicated for you because molality is abbreviated as a lowercase m. And it is related to moles. Okay, so the main selling point of molality, it's also why I lowercase this, is that it is temperature independent. We are literally going to do a lab in the second week of labs where we need to use molality, so this will come up pretty quickly. Okay, so it is similar to molarity, and honestly, if you had this a solution and you measured it in molarity or measured it in molality, the values will be pretty close. But the main selling point is this has no volume aspect to it, no volume component. Okay, so this is known, or this is translates to moles of solute per kilogram of solvent. So we don't care about the total volume of the solution or even the total mass. We care about just how much solvent you have. So if you have salt water, we want to know how many moles of salt divided by how many kilograms of water. Okay. So let's try that example we did last time. We did this one, the 35.7% weight of sulfuric acid when we converted it to molarity. Let's do the same thing, but let's convert it to molality. Okay. Just keep using the same example because we have some level of familiarity with it. Oh yeah, the other problem I have with molality. If you have a molarity solution, this would be 4.26 molar is how you pronounce that. How you would pronounce a solution with a given concentration in molality is molol, which sounds weird. Basically sounds like I have a speech impediment when I don't. Okay, so we said that for percent by mass, there are two ways to interpret this. This one is useful for molarity. This one is useful for molality. Okay, so the way to think through this is if we had 100 grams of this, that would be 35.7 grams of H2SO4. Okay, nothing too weird, nothing unexpected, exactly what you'd think. If we had 100 grams of solution, we could figure out how much of that is the solvent, which is what we care about this time. So you take 100 minus this, and you would get 64.3 grams of H2O. So this number, just for anybody trying to keep track, is the 100 grams we assumed to give us 35.7 minus the 35.7. Okay, showing my work. Now, our goal is similar to last time. We're basically just like this. This needs to be converted to moles, and this needs to be converted to kilograms. Okay. We don't actually need the density for this one because we have grams, and we can convert to kilograms without any volume component. So there is no temperature dependence because everything is masses. Okay. The converting from grams to moles is going to be exactly the same. We already figured that number up in the last video. It's 98.078 grams per mole of H2SO4. Okay, that feels exactly the same as the last problem. The next step is we need to convert from grams to kilograms. We need kilograms on the bottom, so there are 1,000 grams in a kilogram, and that's literally the entire process. So in some ways, this almost feels a little bit easier. So if you take 35.7 divided by 64.3, hit equals, divided by 98.078, hit equals, times 1,000, hit equals, you get 5.66 molol H2SO4. So we saw on the other problem where we were solving for molarity that this came out to 4.26, this is 5.66. They are not going to be exactly the same. Honestly, what I will tell you is the lower the percentage is, the closer these two numbers are going to be. 35.7 is a pretty high percent, so these numbers are pretty different. Okay, so this one is really, really important for one of the labs that's going to be coming up. Please, please make sure you understand this and ask me questions if you need help. All right, thank you.